Hello friends, greetings of the day. In today's video session on design of machinery elements, we'll be learning about how to determine the stresses or the dimensions in case of combined loading. When I mean to say combined loading, it is a combination of axial load, bending load and torsional load. We'll be trying to understand how these loads behave individually as well as in combination. Let us start our session. Let us see an example. A bar of 50 mm diameter fixed at one end is subjected to a load of 1 kilonewton meter. In addition to an axial pull of 15 kilonewtons. Determine the principal stresses if the length of the shaft is 250 millimeters. So in this numerical, it has been clearly asked to determine the principal stresses, nothing but the maximum normal stress and the minimum normal stress, sigma 1 and sigma 2. This numerical or this example is a combination of axial plus torsional loading. Let us now start solving this numerical. Let us start with the given data. In this numerical, a diameter of 50 mm has been given and also the torque MT is given as 1 kilonewton meter, which is nothing but 1 into 10 power of 6 newton mm. Here kilonewton and meters has to be converted. Kilonewton will be converted to newtons and meters has to be converted to millimeters. Also, an axial force of 15 kilonewtons, which is equal to 15 into 10 power of 3 newtons, is given in the numerical. At the same time, the length of the entire bar is 250 mm. This numerical or this component is subjected to axial and torsional stress. The related formula for axial and torsion stresses are given in the following equations. Sigma maximum, sigma minimum, which we call it as maximum and minimum principal stresses. At the same time, we can also determine the maximum shear stress by using the following formula. Let us now find axial stress sigma A, torsional stress tau separately and start using the following equations. To find axial stress, we will be using the equation sigma A is equal to F by A, where A is given by pi d square by 4. Therefore, sigma A is equal to F by pi d square by 4. By substituting the values of D as 50 mm and F as 15 into 10 power of 3 newtons, we will be able to determine the axial stress. The value of axial stress sigma A obtained by using the above equation is 7.639 megapascals. Let us now find the torsional stress given by the equation tau is equal to mt by z naught. In this case, mt is called as torque, which is already given in the numerical, and z naught is called as polar section modulus. This polar section modulus is obtained from the design data handbook from table number 2.2, which is given by this following equation pi d cube by 16. Now substituting these equations, the values given in the numerical, will be able to obtain the torsional stress tau is equal to 40.743 megapascals. Now we have determined axial stress as well as torsional stress. We will be using the equations of combined loading. Let us now determine the combined stresses. The value of axial stress is 7.639 megapascals and the torsional stress is 40.743 megapascals. To find the maximum principal stress, we'll be using the following equation. Sigma maximum is equal to sigma a by 2 plus root of sigma a by 2 whole square plus tau square, where sigma a is called as axial stress and tau is called as torsional stress. By substituting the values obtained, we'll be getting the maximum principal stress as 41.11 megapascals. Let us now determine the minimum principal stress. The minimum principal stress will have the formula as sigma a by 2 minus root of sigma a by 2 whole square plus tau square. Let us now substitute the value of sigma a and tau in this equation to determine the minimum principal stresses. After substituting these values, the minimum principal stress obtained is minus 37.733 megapascals. Since there is a negative sign, it indicates that the minimum principal stress is compressive in nature. Let us now determine the maximum torsional stress. The maximum torsional stress is given by the equation root of sigma a by 2 whole square plus tau square. By substituting the values of sigma a and tau, we will be getting the maximum shear stress value as 40.922 megapascals. So that is how we will be trying to find the combined stresses by using these equations. Let us now look into one more example where it is a combination of bending and torsion. In our previous example, we had seen the combined effect of axial and torsion loading. So in this example, we will be seeing the combination of bending and torsion loads. In this example, it has been given that a round rod of 60 mm diameter is subjected to a bending moment of 900 Newton meter and also a twisting moment of 1200 Newton meter. We need to determine the maximum normal and shear stress induced in the rod. Let us start this numerical by writing down the given data. The diameter of the rod given is 60 millimeters. The bending moment is 900 Newton meter equal to 900 into 10 power of 3 Newton mm. The twisting moment or the torque is given as 1200 Newton meter equal to 1200 multiplied by 10 power of 3 Newton mm. Let us now determine the stresses induced by using the following equations. Sigma 1 or sigma maximum is nothing but the maximum normal stress given by the equation sigma b by 2 plus root of sigma b by 2 whole square plus tau square. In this equation, sigma b is called as bending stress and tau is called as torsional shear stress. Also, the maximum shear stress is given by the equation tau maximum is equal to root of sigma b by 2 whole square plus tau square. And the bending stress sigma b can be found by using the equation sigma b is equal to mb by z, and torsional stress tau can be obtained by the equation mt by z0. Let us start finding bending stresses. The bending stress is given by the equation sigma b is equal to mb by z, where mb is called as bending moment and z is called as section modulus. The equation for section modulus can be obtained from table number 2.7 from Design Data Handbook. For circular cross section, the value of Z is given by pi d cube by 32. By substituting the values of MB and D in the following equation, we'll be able to determine the value of bending stress. After substituting, we'll be getting the value of bending stress as 42.441 megapascals. Let us now find torsional stress and substitute both bending and torsional stress in the equations. The torsional stress equation can be obtained by using tau is equal to mt by z naught, where mt is known as twisting moment or torque and z naught is called as polar section modulus, which can be obtained from table number 2.2 from Design Data Handbook. The equation for Z naught from the data handbook is given as pi d cube by 16 for a circular cross section. Therefore, the equation for tau is given as mt by pi d cube by 16. By substituting the values of torque and diameter, we'll be able to determine the torsional stress, which is given by the value 28.294 megapascals. Let us now find the combined effect of bending and torsion. The bending stress obtained is 42.441 megapascals and the torsional stress obtained is 28.294 megapascals. We'll be using these values in the main equations sigma maximum and tau maximum. In this numerical, there is no necessity of determining the value of sigma minimum, because in the numerical it has been asked only to determine the maximum normal stress and maximum shear stress induced in the rod. Let us now use the equation for maximum principal stress. By substituting the values of sigma b and tau in the above equation, we will be able to determine the sigma maximum value as 56.587 megapascals. Since the value is positive, it is understood that this stress is tensile in nature. Let us now determine the maximum shear stress. The maximum shear stress can be obtained by using the equation tau maximum is equal to root of sigma b by 2 whole square plus tau square. By substituting the values of sigma b and tau, we will be able to obtain the value of maximum shear stress as 35.367 megapascals. Let us now look into one more example of combination of bending and torsional loads. This example is almost similar as the previous example, except that in this numerical we need to find the stresses at critical points. Whenever we talk about critical points, we'll be talking about the top layer A and the bottom layer B, or we can usually call it as the top layer T and the bottom layer B. So here in these areas we'll be able to determine the stresses. In this numerical, he has given us a circular rod fixed at one end having a diameter of 60 mm and length as 300 mm, is subjected to a torque of 3 kN and a transverse load of 5 kN at the free end. We need to determine the nature and magnitude of stress at the critical points. The diameter of the rod is 60 mm. The torque is 3 kN meter equal to 3 into 10 power of 6 Newton mm. The bending load applied is 5 kilonewtons, which is nothing but 5 into 10 power of 3 newtons. The length of the rod is 300 mm. This is the data which is given in this numerical. The type of stress is the combination of bending and torsion, where to find the maximum and minimum principal stresses we'll be using the following equations. Let us now determine the bending stress. Bending stress can be obtained by the equation sigma b is equal to mb by z, where mb is called as bending moment. mb can be further determined by using the equation force into perpendicular distance, or force multiplied by the total length of the rod. In this case, the force is given as 5 kilonewtons and the length of the rod is given as 300 mm. So by using this following equation, we'll be able to determine the bending moment, and the value of Z for a circular rod from Design Data Handbook table number 2.7 is given as pi dq by 32. Let us now calculate the bending stress. So sigma b is equal to force into perpendicular distance divided by the value of Z, which is pi dq by 32. On substituting the values, we'll be determining the bending stress as 70.735 megapascals. Let us now understand how this bending stresses will be acting at the top layer as well as at the bottom layer. At the top layer, the bending stress will be tensile because of bending, when it bends here, the top layer is extended and the bottom layer gets contracted. So because of this, the top layer will be always tensile in nature and the bottom layer will be compressive in nature. Let us now find the torsional stress, and later we'll be trying to combine bending and torsion. To find the torsional stress, we'll be using the equation tau is equal to mt multiplied by z naught, where mt is called as torque, which can be obtained by the equation force multiplied by radius, but in this case the torque is already given as 3 kilonewton meter, and z naught from data handbook can be obtained using the formula pi dq by 16, which can be obtained from table number 2.2 Design Data Handbook. So let us use this equation tau is equal to mt divided by pi dq by 16. By substituting these values of tau, we'll be able to determine the value of tau as 70.735 megapascals. The effect of tau will be same throughout the section. So we'll not be trying to calculate the value of tau at top layer as well as bottom layer. Since it is a twisting moment, the twisting moment will be almost same at every part of the section. Let us now determine the effect of combined stresses, and also we'll try to determine the stresses at the critical points, that is the top layer as well as at the bottom layer. So bending stress obtained is 70.735 megapascals, and at the top layer it is tensile in nature, and at the bottom layer the bending stress is compressive in nature. The torsional stress obtained is also equal to 70.735 megapascals. We'll use these values to determine the maximum principal stress at top layer. The equation for maximum principal stress is given as shown on the screen. By substituting the values of sigma b and tau for the equation, we'll be able to determine the stress sigma maximum value as 63.93 megapascals. At the same time, let us find the maximum principal stress at bottom layer. The maximum principal stress at the bottom layer can be obtained by substituting the value of sigma b as minus 70.735 megapascals, because at the bottom layer the bending stress is compressive, so we are trying to use the negative sign in this equation. By substituting these values, we will be getting the maximum principal stress at bottom layer as 43.717 megapascals. Let us now determine the minimum principal stress at top layer and bottom layer. The minimum principal stress can be given by the following equation. By substituting the value of bending stress sigma b and torsional stress tau, we will be able to determine the value of minimum principal stress as minus 43.717 megapascals. Since it is negative, it can be clearly understood that the minimum principal stress is compressive in nature at top layer. Also, let us determine the minimum principal stress at the bottom layer. By substituting the values of bending stress at the bottom layer, we will be able to obtain the minimum principal stress as minus 114.451 megapascals at the bottom layer. Let us now determine the maximum shear stress at top layer as well as bottom layer. The shear stress at the top layer is given by the equation tau maximum is equal to root of sigma by b by 2 whole square plus tau square. By substituting the values of sigma b and tau, we will be determining the maximum shear stress as 79.084 at top layer, and by using a similar procedure we will be able to determine the maximum shear stress at the bottom layer as 79.084 megapascals. Since here the values are almost similar, the shear stress at top layer is almost same as the shear stress at bottom layer. In this numerical, we will be determining the maximum compressive and shear stress in an hollow shaft subjected to axial, bending and torsional loading. A hollow shaft of 40 mm diameter and 25 mm inner diameter is subjected to a twisting moment of 118 Newton meter. It is also subjected to an axial thrust of 9,806 newtons and a bending moment of 79 Newton meter. Let us calculate the maximum compressive and shear stress. The following data is given in this numerical. The maximum diameter of the hollow shaft is given as 40 mm. The inner diameter D2 is given as 25 mm. The shaft is subjected to a torque or twisting moment of 118 Newton meter. The axial thrust applied on the shaft is 9,806 newtons. The bending moment applied is 79 Newton meter. By using the following equations for maximum principal stresses and maximum shear stress, we will be trying to determine the effect of combination of axial, bending and torsion loads on this hollow shaft. Let us now start finding the effect of individual stresses. The axial stress can be obtained by using the formula sigma A is equal to F by A. The value of F is clearly given in this numerical as 9806 newtons, and area can be determined for the hollow shaft using this equation pi d1 square minus dt square divided by 4. By substituting the given values in the numericals, the axial stress obtained is 12.805 megapascals. Since it is axial thrust, the axial stress obtained will be compressive in nature. Let us now determine the bending stress. A bending moment of 79 Newton meter is applied on this component. The bending stress can be obtained by the equation sigma b is equal to mb by z. The value of mb is already given in the numerical. Let us now find the value of z, which is nothing but section modulus. The section modulus for hollow shaft can also be obtained from table 2.7 from data handbook. The equation for z is given as pi d1 power 4 minus d2 power 4 divided by 32 d1. By substituting the values given in the numerical, that is the value of mb, the value of d1 and the value of d2, we'll be able to determine the bending stress as 14.837 megapascals. Let us now determine the torsional shear stress, which is given by the equation tau is equal to mt by z0. In this case, z0, which is nothing but the polar section modulus, is given by the following equation. The value of mt is given as 118 Newton meter. By substituting these values, we'll be able to determine the shear stress or the torsional shear stress as 11.080 megapascals. Let us now determine the effect of axial and bending stress, which is given by the equation sigma AB is equal to sigma A plus sigma B. By substituting the values obtained, we'll be getting the value of sigma AB as 27.642 megapascals, which will be compressive nature because axial stress is also compressive because it is the axial thrust which is applied on the shaft. At the same time, bending stress can be tensile at one layer and compressive at other layer. Since in this numerical we are supposed to calculate the maximum compressive stress, so the value of sigma A and sigma B will be in compressive nature, and since they are both are in compressive nature, we are adding those values and thus we will be getting the value of 27.642 megapascals, which is also compressive in nature. Let us now determine the maximum compressive stress by using the following equation. Sigma AB is equal to sigma AB by 2 plus root of sigma AB by 2 whole square plus tau square. By substituting the values obtained, we will be able to determine the maximum normal stress as 31.535 megapascals. Let us now determine the maximum shear stress by using the following equation. The maximum shear stress obtained is 17.714 megapascals. In this example, let us understand the effect of combined loading, that is, the combination of all the three loads: axial, bending and torsion. A circular rod fixed at one end, having a diameter of 50 mm and length 250 mm, is subject to a torque of 1 kN meter. It means that there is a twisting moment of 1 kilonewton meter, and also the rod is also subjected to an axial load of 15 kilonewtons and a transverse load of 3 kilonewtons at the free end. We need to determine the nature and magnitude of stress at critical points. As we have already discussed, whenever we talk about stress at critical points, we will be considering the top layer and the bottom layer. Finding the stresses individually at top layer and bottom layer, we will be trying to determine the stresses at the critical points. Let us solve this numerical by writing the given data. In this numerical, the diameter of the rod is given as 50 mm. The length of the rod is given as 250 mm. The torque MT is given as 1 kilonewton meter, which is 1 into 10 power of 6 Newton mm. The axial tensile load is given as 15 kilonewtons, equal to 15 into 10 power of 3 newtons, and a transverse load of 3 kilonewtons has been given, which amounts to 3 into 10 power of 3 newtons. To find the combined stress due to axial, bending and torsion, the following equations will be used. Let us now find the effect of individual stresses or individual loading. Let us start with axial stress. Axial stress can be given by the equation sigma A is equal to F by A, where A is the area of the cross section, which is given by pi d square by 4. Therefore, sigma A is equal to F by pi d square divided by 4. By substituting the data given in the numerical, we will be able to determine the value of sigma A as 7.639 megapascals. The effect of axial stress will be same at the top layer as well as at the bottom layer, because its effect will be tensile in nature. Therefore, at top layer, axial stress is tensile in nature. At the same time, at bottom layer, axial stress will also be in tensile in nature, because the layers at the top fiber as well as bottom fiber both extend because of axial pull. Let us now determine the bending stresses. The bending stress is given by the equation sigma b is equal to mb by z. The equation of z can be obtained from data handbook. For a circular cross section, z is given as pi dq by 32, and bending moment mb can be found using the following equation: force into perpendicular distance, or force multiplied by the length of the rod. So using the given data and substituting in the following equation, the value of sigma b can be obtained as 61.115 megapascals. Once again, let us understand the effect of sigma b at top and bottom fibers. At the top layer, there will be a tensile stress due to bending load, because the top layer tends to extend. But in case of bottom layers, there will be compressive stress, or the bottom layers will be compressive in nature because of sigma b. Now if you see here, the bottom layers will be subjected to contraction. Since it is getting contracted, the stress will be compressive in nature. Let us now determine the torsional shear stress, which is given by the equation mt by z0, where z0 is polar section modulus and is given as pi dq by 16 for circular cross section. The equation can be obtained from table 2.2 from Design Data Handbook. By substituting the given values in the numerical, we will be able to determine the torsional shear stress as 40.743 megapascals. Let us now determine the combined effect of axial and bending stress alone, which is given by the equation sigma AB is equal to sigma A plus sigma B. Now let us find this effect individually at top layer as well as at bottom layer. At top layer, the equation is given as sigma AB is equal to sigma A plus sigma B. This is because at the top layer, the axial stress will be tensile in nature and bending stress is also in tensile in nature. So we are going to add axial as well as bending stress. So by substituting the obtained values of sigma A and sigma B, we will be getting the value of sigma AB, that is nothing but the combined effect of axial and bending stress as 68.754 megapascals. So this combined effect of axial and bending will also be tensile in nature. Let us now understand the effect of axial and bending stresses at bottom layers. At bottom layers, the equation is written as sigma AB is equal to sigma A minus sigma B. This is because at the bottom layers, the axial stress will be tensile in nature and bending stress will be compressive in nature. Therefore, by substituting the obtained values of axial and bending stresses, we will be able to determine the effect of combined loading axial and bending stress. The value obtained is minus 53.476 megapascals, which it is clear that at bottom layer the stress is compressive in nature. Let us now determine the maximum and minimum normal stress as well as the maximum shear stress at the critical points, that is at the top layer as well as at the bottom layers. At top layer, the maximum normal stress is given by the following equation. By substituting the values of sigma AB and tau obtained, we will be determining the value of sigma maximum. In this case, the value of maximum normal stress at top layer is 87.685 megapascals. Let us now determine the minimum normal stress, which is given by the following equation. By substituting the values, we will be able to determine the minimum stress as minus 18.931 megapascals, which is found to be compressive in nature. Let us also determine the maximum shear stress by using the following equation. By substituting the obtained values, we will be getting the maximum shear stress as 53.308 megapascals. Now let us determine the maximum and minimum normal stress as well as maximum shear stress at bottom layers. By substituting the obtained values, the maximum normal stress obtained at the bottom layer is 21.995 megapascals, which is tensile in nature, and the minimum normal stress obtained is minus 75.471 megapascals, which is compressive in nature. At the same time, the maximum shear stress can be determined by using the following equation, and after substituting the obtained values of sigma AB and tau, the maximum shear stress is 48.733 megapascals. Thank you friends for watching this session. Make use of this session and start practicing the numericals. We'll be meeting in the next session with some more new numericals. Till then, have a nice day.